this started. I think OBS is actually behaving. It's mind-blowing to me. All right, so today is October 3rd, 2024. We're here at ASU in CSE466. We are just kind of halfway through, starting on. I didn't change the title again, so it's still wrong. I just copied the previous one. It says dynamic heap exploitation, but it would be dynamic allocator misuse or heap misuse, or I'll even take heap exploitation 1. Like all of these are all, word salad. All goes to the same place. Memes. We didn't get a whole lot. We never get a whole lot on Thursday. That's why Thursday is a good day to show up, because we actually talk about things. Lore. So if you just decided to randomly Google heap exploitation on Linux or CTF heap on Google, I loosely referred to this on Tuesday or alluded to it. There's a whole lot of stuff behind the T-cache. Nothing in this module requires it. Most of the tricks that are slides on Twitch not updating. I was so confident in OBS for a moment. OBS. I was such a believer. Then it was all a lie. All right. So you missed a lot. Thank you for mentioning the slides are busted. But all of these more complicated heap mechanisms that interact with various bins and deeper parts of the heap, they are known by some kind of shorthand. A lot of them are referred to as house of something. So there's house of lore, house of spirit, house of bot cake. And these are ways to refer to specific techniques of heap exploitation. You don't need any of those for this module. So if you are going down, which is interesting and fun to learn about, but if you are going down that road thinking that you're going to use it for this module, it definitely is not the intended path. It wouldn't surprise me if there's some unintendeds there. I haven't gotten out of my way to stop you from using these things, but it's not what you're supposed to be learning. Twitch seems to like it when I say things for them. That's pretty awesome. I know other instructors don't. If this is your general take on this course, hey, I go through, get past the checkpoint, hit something hard and stop. That's awesome. Go for it. That's why the checkpoint's there. You know there is something hard now, right? There was some cruise through easy point. You got stuck. Then we go through it. And then in general, I've noticed that there's just the giant flood of CSE memes. If you missed it, I gave Sam, one of the TAs here, liking meme power. So go placate, post memes that make him happy, in case I'm missing them. Soon TM. So one of the things I've said for several weeks now is that there's going to be this great, amazing extra credit live thing. It isn't all just me saying useless things on camera here for you. Meant it totally as in once you can demo some more, and I'm not sure what you're going for there, Twitch chat. Say it again. But extra credit stuff, at this point there is a PR that's on our public GitHub that is the implementation of that. I'm waiting for other people to tear it apart and tell me that they hate my code. If I don't get any major request for refactor, I'll probably merge it in tomorrow evening. At which point, congratulations, extra credit will be live on the dojo for hopefully everyone. But part of me debugging that is I play with, I dev on prod, as everyone should. And so you probably saw me thanking myself for liking my own memes that weren't memes. And that was just me verifying behavior works from the live Discord and communicates where it should. So we said, next week meme. Lack of homework will be getting to me to try and leak the stat. I still don't know what you're going on about, Twitch. I'm glad you're up at 2 a.m. working on this. With that is all I have. This is why Thursday is awesome. All right. Tuesdays we can end up with 30 minutes of slides and me rambling. Or Tuesdays. Thursdays, boom, 4 slides. We're done. So we're going to get to some demos. What are you guys stuck on? I haven't looked at where your progress is. These are some things I think are useful to talk about. But is anyone stuck on something in particular? And I guess more importantly, have you watched Jan's videos? Because that was a problem on Tuesday, so I had to reiterate stuff that was kind of already there, just to make sure that it was applicable. So does anyone have anything specific you want me to try and touch or hit on? I have this super generic, amazing binary that probably has bugs I don't know about that I'm going to use as a prop probably for the rest of this module. If nobody has anything, I'm just going to get right to it. All right. So we'll start up some random challenge here. What are we? Dynamic, allocator misuse. Connect to the old dojo. Give me one quick moment. I do see Twitch chat trying. Someone says they're stuck on 7. Seems the secret key needs to be 10 bytes, but puts only outputs 8. So I am still, despite what I did on Tuesday, I'm not going to try and solve literal challenges that are there for you. What I would say there is puts does not have a restriction of 8 bytes. When does puts stop printing things to the screen? Anyone know? Null byte, because it prints a string. So somehow you are getting a null byte after 8, which does make sense. Ask in Discord, other people want to help. Great. Okay, somebody says, question. Leaking stack and main address when the heap isn't contiguous. So the heap itself is a contiguous region of memory. Let's start there. All right, so I made this amazing binary. It's probably that's large enough. It's very similar to how these challenges work. Most heap challenges follow this type of a format where you're presented some type of menu. Maybe they disguise it as an address book or a phone book or something where you can perform these operations. All right, you can perform a malloc, a free, a read write, puts, and then I have a couple other options here. Now, the statement on Twitch here was that the heap is not contiguous. The heap itself is contiguous. So if I grep for a.out here, and I attach GDB, so sudo GDB A156, I'm now on that binary. If we type VM map, everything on the heap is located in this region of memory that is called the heap, right? They may not be right next to each other, but they are in fact contiguous. Now, if your issue is that your chunks are not right next to each other, well, that has to do with the order of operations that you are performing. So, for instance, if I were to malloc something, we'll put it in slot 0. Let's malloc something of size 64. We'll malloc something again. We'll put it in slot 1 of size 64. And then we malloc a third thing of size 64. That's great. Now, the order that I free these matters if I care about where they are located. Okay, wait. So the statement is, they're correcting me. They do understand the heap is contiguous. The heap isn't contiguous with the stack and or main. So that is true. If we look here, the heap itself is not contiguous with our binary. It isn't contiguous with our elfin memory. And the heap is certainly not contiguous with the stack. And so you getting a leak of the heap only informs you about where things are on the heap, right? Where the heap is. If I want to, and I don't believe this is necessary, but we can do it anyway since you're asking. If I wanted to know, is it possible for me to leak something on the heap that tells me the stack? If you have Jeff, I'm sure pwn.debug has a similar command. Is that the right command? Hopefully. Okay, it is the right command. I just wasn't in an actual GDB prompt. So Jeff provides a command called scan. Scan is super helpful. What you're doing here is you are looking for pointers to a region in a region. So when I say scan heap stack, it says I'm searching addresses in heap that point to the stack. There's nothing in my binaries heap that point to the stack. Now, what if I did the reverse? The answer is there are pointers on the stack that point to the heap. This doesn't solve your problem, Twitch chat, and this makes sense. The behavior of my binary is I'm calling malloc, I'm storing that pointer in some local variable, more than likely. Maybe it's a global, but in this case, it's probably on the stack. I'd have to look at the source to see where I put it. But all of these addresses on the stack hold a pointer to the heap. So what this is showing me is here's a stack address. Here is the value that is at that memory location. This is extremely useful if you are trying to, the terminology typically used here is pivoting around memory, because you have those contiguous blocks of memory. And so if the only thing I can leak is heap stuff, well, can I, let's scan the heap for something that points to a.out. Now, why did I say a.out? Why didn't I say elf? So scan is actually not that fancy of a complicated of a tool. What it's doing here is it's grepping the names over here on the right-hand side. And so when I say a.out, it's anything over here that has the string a.out. Right? That's what it's searching for. You can pass literal address ranges to scan as well. And there are cases where you may want to do that. I don't believe that's needed in this module. So we weren't able to, on my example binary, if I can leak stuff on the heap, I couldn't get a stack leak in its current state. Maybe I can perform more operations and that would change. But what I can get in the current state is I can scan the heap for anything that is in this range, right? That's contiguous with the binary itself. And we see right now on the heap, and I haven't done anything like particularly crazy, right? I just malloc a couple things. There are addresses on the heap that hold pointers into my elf. I don't know the specifics of your challenge here, Twitch, but does that help you as far as what you're thinking about there? Give it a moment. Does this make sense to everyone here, what scan's doing? Sweet. All right, I got nothing from Twitch, or it's like the world's longest delay. Sweet. So I malloced three things here in 0, 1, and 2. They're all size 64. If I care about the proximity of them next to each other, the order that I free and malloc matters, right? That the heap is actually deterministic. People don't realize that at first glance. Now, the heap may be based somewhere arbitrarily due to ASLR, but the distance between the first 64-byte allocation and the second 64-byte allocation is known. And so if you have any series of actions, series of mallocs and frees, you can deterministically say the 50th malloc is going to be so far away from the 130th malloc, assuming you know all of the operations. It's just a matter of getting to that state that you are trying to analyze and then examining it in GDB or using something like ltrace. On the point of GDB, I've malloced three things, and I don't really care that they've been malloced. One of the things that I showed was heap chunks, and it gives us this pretty output of where these chunks are located in memory. And that's great, but what if I want to have a different perspective? I want to make sense of what this looks like. Well, we can use tools that we already know. So I can say examine, how many do I want? 8 for 64, let's do 10, let's do 14. Examine 14 giant hex. And this pointer that I got right here, D1AC0, was my first allocation. All right, it's not particularly interesting, right? Because we haven't put it anywhere. We just asked for memory. Let's read into index 0. Let's read 8 bytes. Let's put some A's. 1, 2, 3, 4, 5, 6. Can I count? 1, 2, 3, 4, 5, 6, 7, 8. I'm going to hit Control D. One thing to be aware of, in this case it was 8 and 8, so it wouldn't have mattered. If I, for instance, put 20, and then when I'm interacting with the challenge, I use send line, or if I'm on the terminal, I AAA and hit enter, what's going to happen? It's going to put that hex OA. It's going to put that new line character. That may or may not impact what happens. In my play binary here, I have puts. So I could put index 0. I get A. Why? Because there's a terminating null byte to go back to what Twitch said. What happens if I instead write from index 0 and I write, I don't know, 100 bytes? Okay, so I didn't have a new line, so we just, here's my A's. There's this Q here, and then this is the help text. It didn't give me a new line. Makes sense, there's no new line there when we did write. So far, not super interesting. What happens if I read in index 1? Let's read in, again, 8 bytes. Let's put B. Okay. And then let's do that same thing where we write out from index 0, and let's do 100 bytes. Does anyone have any idea what we think we might see? Any guesses? And why? Nothing. Cool. So we see A. We get that Q again. And then we see the B's. What happened? What did I do? Why do I see the B's? I put the B's in index, the heap allocation on index 1. Yes?
Is it because there's no null byte between them?
So if the statement for Twitch was, is it because there's no null byte between them? That's a good theory, right? And if I was using puts, we see that there is the A stop. Puts stops at a null byte. But when I use write, when this may seem backwards, write is literally displaying it to the output because it's performing the write syscall. Read is reading into memory. So it's writing to the allocation when I call read. Deal with it. But if I call write on index 0, it asks for a size, because write doesn't care about this being a string. Write doesn't care about what the values of these bytes are. Write just says, give me a number, and I'm going to just throw those bytes to the screen to stand it out. And so when I say write 100, I'm writing 100 bytes starting at my first allocation. My first allocation was at 1C0, which is this place right here. And in my heap chunks output, we see 61616161. What is that? And then there's null bytes. There just happen to be null bytes. It's not like I set it to be null bytes. And then what is after that chunk in memory? So this is my index 0. This is my index 1. It ends in 1B0. It's right after it, right? It's 64 plus 16. What is that? 70, 80. It's 80 bytes ahead. And so when I say write 100 bytes, I'm starting from this location, or this location. We see all of these A's. It actually is writing out all these null bytes, but the null bytes don't display at my terminal, so that's kind of a no-op. And then we keep writing bytes until we are writing bytes from the second allocation, despite me printing out from the first memory address. Does that make sense? Yes. Okay, so this is like the read equivalent of a buffer overflow, right? It's an overread. And we can use an overread to read information from other chunks. But it isn't particularly interesting right now because the values that are on these chunks and that are being used are user values, right? These chunks have been allocated. What's way more fun is if we do the same thing, but we do it on free chunks. So let's free index 1, and then let's write from index 0. So we're freeing the one that's ahead. We're going to write from the one that's earlier. We're doing that exact same thing, and I'm going to write out 100 bytes. But now I get something a little bit different. We still get A. We still got this Q, but now I've got squiggly C. Where did that come from? What is it? Why did squiggly C appear there? I put B, 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 B. In fact, my B's are gone. Why are my B's gone? All I did was I malloc to put my B's there, and I freed that bad boy. And just to show that this isn't like a trick, I should be able to, for instance, write from index 1, write my 8 bytes. This should be my 8 B's. What happened? How are these chunks used when they're free? This is what Jan's whole video and why we draw pretty pictures. So the chunks are reused when they're freed to store metadata. So right now I have 2 chunks. I technically have 3, but there's only 2 that matter here. We have B, which has been freed. We have A, which is right here. A currently has a bunch of A's in it. B has been freed. What happens when I free a chunk? What does it put there? There's 2 things ahead. Well, there's a next pointer. What's the value of the next pointer if I freed this? And it's the only allocation. What's that? Null, right? We looked at this in GDB when we had heap bins. And what we see is here is my B chunk that I freed. It's chilling on the T cache. It's the only thing in that T cache bin. So its next pointer has to be null. So what happened when I freed it is my B's, which I only had 8, well, that memory location is now being used for the next pointer. So it got nulled out. What other metadata is stored on a chunk? This is the critical piece, right? So there's this next pointer, and B is where the beginning of the allocation is, right? And then this is just kind of a whatever. This isn't used in, this part isn't used in TCAS for singly linked lists. Maybe that shows up. It doesn't say whatever. All right, I wrote whatever after next. Well, what is before the next pointer? Previous size and size. All right, what's the order of those things? Okay, so we're saying previous size and then size. Okay. That makes some sense. That's how this knows that this is however many bytes. We can examine that in GDB. I could examine, for instance, 4 giant hex at that address, and we'll go -10. What do I see? I see, well, this is, am I backwards here? Where's my pointer? B10, B10, so that's my next pointer. That would be my, I believe it's just previous size, isn't it? So let's free another one. Let's take a look here. Right? It makes sense that this is a 5 because these are all chunks that are allocated against 64, which is hex 40. You add 10, the chunk size is 50. The question is this size or prev size? You're saying size, so my prev size is 0. Why is it currently 0?
There was nothing in Tcache.
Well, there's something in Tcache. There's this chunk. Okay, well, let's free index 0. Right? That's the thing that was before it in memory. Right? Okay. And then we will heap bins. I do in fact have two free chunks. This is my first one. So if I examine 4 giant hacks at this location minus 10, that's my first one. And then my second one was the same thing, except it's D1, B10. So we really just have this one guy, right? For these quick singly linked lists, why does this 51 and not 50? Okay, so the least significant, I want to say 4 bits, but we can envision it as the whole nibble, is used for flags, which is what was said here in class. That's how, when we say heap, we have it right there, heap bins, we see previous in use is mmapped non-main arita, right? These are things that can be flagged for a particular chunk. Fortunately, if we're dealing with the T-cache, everything is going to look like this. Everything will be marked. Well, not everything will be marked previous in use, but the previous, assuming the previous came from the T-cache, the previous will be in use. The T-cache is a caching layer, and as a part of the implementation of that caching layer, everything that's in the T-cache is alive, and it is marked as in use. So the reason that both of these, or this guy, B10, has previous in use is because the chunk before it, in memory, in physical proximity to each other, is this one, which is in the T-cache. So if things are in the T-cache, they are considered in use, which is counterintuitive because they aren't actually being used by the program, right? So we have this metadata that we can corrupt, or that we could at least leak. So if I wanted a heap leak, can I do my right trick where I had, where was my garbage? Where I had the squiggle. I had like squiggle C. You guys remember that? Where's squiggle C? Squiggle C here. What do you think that is being leaked out? So I started writing from this location right here. And then this was from writing here. This was AAA. And then we read through this. What is my squiggle C? Let's just do it again. It's malloc back, index 0. I have to let GDB set this guy free. We malloc that back, so now I have it. We will read in to index 0, 8 bytes. We'll give it A, give it a bunch of A's. Okay. And then I will write out from index 0, and we'll do 100 bytes again. Okay. So I get these A's, which makes sense. I put them there. I get this Q. We still haven't figured out what this Q is. We get squiggle C. Q, squiggle C. What are these? Well, this was the address I'm writing from. So let's examine like 20 giant hex from that location. This is what I'm printing. These are the bytes. We got a suggestion here?
Is it the ASCII characters of the data right there? So 51 would be the Q, capital Q.
I actually don't know Q offhand, but that's okay. It's a good theory. So the statement was, hey, is Q hex 51? And it turns out, if we consult the ASCII table here, Q is right here. It is hex 51. So the queue that was being displayed to us from our overread was the metadata right here. So what do you think the squiggle C is? The rest of these are null bytes. We said null bytes, at least when Wright puts it to the terminal here, is basically an op, right? So we're seeing the printable characters of this address. So I could use this to leak out a heap address, right? What else could I do with this?
This is not a Tcache.
What are you asking, or what are you saying?
This memory that we are seeing is not part of Tcache, right? It is part of heap.
Okay, so the statement, this is conflating terms. I'm going to try and deconflate them. The statement from the class here for Twitch was the memory that I'm looking at, that isn't in the Tcache. That's in the heap. Everything that is in the Tcache is in the heap. The Tcache itself, if we do, I think I can do heap bins Tcache to not print out the other garbage. I can. So the Tcache is just a singly linked list, right? It's not like memory moves from heap to the Tcache, all right? The memory address is always in the heap. When we talk about the Tcache, this is like a bookkeeping thing, right? This is the logic of the implementation of how the program, like the code that supports and gives us malloc and free, does the bookkeeping on what is malloc or free. But everything that we look at in memory is going to be in the region of memory that is the heap. So if we grab this right here, we VM map it, we see that is in the heap, right? This is in the heap. If I were to grab this address, that is the first pointer, or the first, let me get this word right, first chunk that is listed in this Tcache bin, and we were to VM map that address, it is also in the heap, right? The Tcache bin is a bookkeeping tracking of what things in the heap are free and what things in the heap are in use, right? So when things are free, we just make a note of it here in the Tcache, but the memory address will always be in this heap region, unless you're doing like really crazy things. So somebody had the observation here that if I start writing from this memory address, we get this Q, and then the squiggle C is the printable parts of this memory address. Are these other bytes of the memory address being output? Someone says yeah. Now I don't get to see them, but what would I want to do if I wanted to capture that? You've probably done this already, right? We printed out some bytes in memory corruption and read them in. What did we use? We used good old pwn tools. So let's start writing our do.py. User bin n python 3 from pwn import star. P is process. My thing is a.out. Okay. Now, one of the things that is a common gotcha is, do I send or do I send line? People still are not quite sure which they should use and why. Does anyone have a clear way of explaining why I should use one or the other? Or is it just try it and see if shit breaks?
Send line just sends a new line character.
Right, that's all it does, right? It's not like send line is a mystery as far as what it does. The question is, which one should I use to talk to this program?
Send line.
Why?
Because it takes one input and then, we have to enter a new line for that input to be processed by the program.
Okay. The statement for Twitch is I should use send line, and then the explanation was honestly kind of jank. All right, like you were just assuming behaviors of the program, right? It does depend. Twitch has it right. It's a bit of an empty statement, but it's correct, saying that if it's just asking for bytes, don't use send line. And if it is, they didn't put this. That's all they put. If it's only asking for bytes, don't use send line. But how do I know? How do I know how this program is doing it? You made this assumption because I was typing it that way, right? Well, we could GDB it. I assume you could GDB it. I assume you could open it up in IDA and hit tab. One other tool that I listed on the slides was something called ltrace. So everyone here has used strace at this point, right? Right. Ltrace is strace's like half brother. Ltrace traces libraries or dynamic library calls. It must be dynamic. It must be dynamically linked. If you use ltrace on a statically linked binary, you'll get nothing. The way ltrace works is it hooks when that call goes into the library. So it's like hooking on the PLT, GLT stuff there. So if I run ltrace, I want malloc stuff on heap a.out. I honestly think, I don't know why I get all this other stuff. I'm probably misusing the filter. But this is how I use ltrace. Someone else could read the man page and tell me what I'm doing wrong. But what we see here is it's now not printing syscalls, but it's printing out library calls. Is it E that I want? Okay, I like this so far. Okay, this is that was nice. And then is that going to give me free as well, or do I got to filter for free? I got to filter for free. Okay. So probably, let's guess this. What I care about is mallocs and frees. Not for what I was just talking about. At this point, I'm just curious. Index. Okay. Index 1 free, selection free, index 1. Okay, yeah, so you can pass multiple E's to do the filter. What I'm interested in, as far as whether or not I should use sendline or not, is this thing calling read or scanf, right? So if it's calling read, the just raw read syscall, read just wants bytes, at which point send is probably what I want. If the implementation of the program is using scanf, does anyone have any idea how scanf works? How can we find out how scanf works? You just did it. Yes, we can read the old man page. So we can man scanf, and if the dojo is firing up correctly, it will describe it to us. So scanf takes a format string, which is a string with some escape characters that define the type that scanf is going to convert this string to. So I, for instance, say scanf %d, it's going to read input until it parses a number, a decimal number. Now, how does it know when that number ends, right? Is it after I type the first one? How does it know if there's another one coming? Or another digit? Because a number could be arbitrarily large, and scanf has to deal with this. Scanf will parse the type specified until a new line or white space character is encountered. If the challenge is taking an input via scanf, you want to, more than likely, use sendline. You could also use send and then just put spaces in between it. So despite the obvious way of working with this thing being I need to type malloc 1 and then 20, I can fire it off altogether and it just works, right? Because what's happening here is when I type in, where's my input? Malloc space 1 space 20, that fires on down standard into this challenge. The challenge is going to say index and call scanf. Scanf is going to, actually it calls scanf, parses the malloc, reaches the white space. It's done. It says index, and then parses a digit, encounters white space, it's done. It says, give me the size, which is this part right here. It parses the 20, it encounters my new line, that's white space, it's done. If I were using send, this is why you should use one or the other, and why if you're using the wrong one and you're blowing up, why it's happening. Different parts, like if I were to call read on this, do you think read Do you think this thing is going to call scanf? No, it's called read. It's going to read. It's going to call literal read. So this thing does not need a new line. It just wants raw bytes. Is it the later ones that use read? The first 20 were just scanf to your knowledge. So this isn't meant to be like a trick. It's not something we purposely did like, haha, there's scanf here. Like scanf is a regular everyday thing that programs do and deal with. So is read. Right? Now, if you strace and something is doing scanf, what will strace show you? The answer was read. Why?
That's the syscall.
Yes, scanf is a library function that calls the syscall read in its implementation. This is why you can't use strace to find out if it's using scanf or read, because everything will just show up as read. All right, cool. So we got to see a little bit of ltrace there. We got to talk about new lines. That was some good stuff, right? What do we got? Twitch. Very annoying how some challenges use scanf and some use read. Yeah, we did it to just be mean. No, it like that is a regular thing that you should like be able to deal with. From every challenge, every module going forward, like the expectation is, and it should be your first step, more than likely, open the binary in IDA or Binja or whatever you want and see what this thing does. Don't assume behavior. The expectation is that you have some kind of reverse engineering skills at this point. So my goal here is to try and leak that address that we saw over here in memory, right? We said, hey, if I malloc two things and then I free it and then I overread, we should be able to get that memory in our script. So let's do that. What were the order of operations that I did? Okay, I malloced. 0. 64. Another PWS send line. We do the same thing. Cool. I got that. I got 2 of these. What am I doing now?
Should be the second for index 1.
So this one should be in 1 instead of 0. That was a good catch on me. What's my next action? I malloc. I free, right? Why do I need to free it? To get it into the T cache. Now, getting it into the T cache, what does that do? It gives me the next pointer, right? What's the next pointer going to be right now, just looking at this? It's going to be null. So how do I want to fix it? Because I want to actually leak out something. Leaking out null would be pretty boring for a demo. Let's leak out something of value. How do I get something of value in the next pointer? What do I got to do? I free it again? We can free it again. This is going to be a great learning moment. Okay. Oh, don't free again. Free 0. Okay. I free 0. Now what do you want me to do? And why did I free 0?
So that it overlaps.
Overlap?
So sorry. No, it points to the next point.
Overlap is a problem we'll talk about next week. That one gets fancy. All right.
So the next pointer points to 0 points to 1.
Okay, so if we understand how the T-cache works as a singly linked list, everything as we free it gets pushed onto the head of this list. So without using GDB and without printing this out, we should have a working mental model of what's happening here. I'm going to grab 2 chunks, assuming the T-cache for this bin size is empty. These should be fresh off the heap, right? So these are going to be right next to each other in memory because the heap is deterministic. The glibc heap is deterministic. Not all heaps are. And then when I free 1, that's going to put it on the head, the first entry on that T-cache list. When I free 0, what happens?
This becomes the head and the previous one becomes next.
All right, so the statement was 0 becomes the first guy the head points to, and then 0 gets a next pointer that points to 1. Okay, so now what do I want to do to get that next pointer? You want me to read? Okay, so you want me to write. Oh, yeah, I still want to send line. We're going to write. I'm going to write from where? Where to where? You want me to write from 0? I can do that. In fact, this should be super boring, but we can do it.
Do we need bytes for 364?
So we don't need the 64 there. That's a good call. So we were thinking about things right. Now this will work because we are assuming, we're making an assumption here about this, the behavior of this binary. What are we assuming? This will work. We can do it. Let's p receive. Does this thing say anything when we write? Let's get GDB off of that. Yes. Okay. We'll receive until. Let's receive all with a timeout. Oh, I don't want to receive all. What do I want? Receive repeat, I think. Timeout, give it like a second. Oh, let's just clean. That's even way better. Okay. P clean will send right, and then I'm going to receive until, what do we got? Slot 0. Will P receive line, because we're getting up to this end of line right here. And then let's P receive until right. That makes sense, right? Yeah. And then I'm going to throw on, because I'm not entirely sure what's going to happen here. We're going to import IPython, and we'll embed IPython.
Why don't you write 8 bytes? Like, why not more than 8?
So we're not doing what I was saying over there. We're actually doing something else, and hopefully we'll see why. We'll run our do.py. I got this. What's my leak? Okay. So I only needed to print 8 bytes. Here's my address. This goes back to the what am I assuming? Why does this work? You actually didn't do the same thing I did. Let's think about it. So we have to think about not only the order that we're freeing things, but where are these pointers in memory, contiguous to each other. What we did here is we have two chunks. We have an early chunk, right? This is the first one. He's earlier in memory. This is the first thing that's allocated. We have the later one. We then freed the later one. We then freed the early one. So, when we write from 0, where is the next pointer? The next pointer is literally right there. We're using a use after free here. We aren't overwriting. We're assuming that the binary doesn't null the pointer. Do you see what we did? There's some thinking. I got a head nod there. There's like this is important to know because like I can add one line here and this whole thing will break. Because I added this like really cool thing because I thought about that you might end up doing this. Toggle null. You know what that does? That makes this binary null after freeing, which is a sane and reasonable thing to do. So this binary does have a use after free vulnerability, and that's what we used to leak out this memory address. And we could, I assume people could say, give me leak, what do I want? 6 bytes, and then we'll ljust it to 8 with null bytes, and then we U64 does that. What did I miss? Bam. And then we hex it. Okay, that's my heap leak. Right? We were able to do that. We got a heap leak. We did something. Somebody says, very annoying. Oh yeah, that is a you problem, not a us problem. Later ones use these. Don't remember, but I think I struggled a lot with heap stuff at first because I didn't understand how scanf worked and just assumed it worked like read. Yeah, well, one of the things that will repeatedly bite you in this type of content is assuming things, right? There's documentation. Go read it. So we got this this next pointer, right? But we assumed that we had a use after free, which it does. If I, before this, do p send line toggle null, but all that does is make the binary null it out after it frees.
So you won't get it.
Oh, leak. All right. That doesn't work now because now that's been nulled out. Can I still get that next pointer? Yeah, we can do what I originally said. So how do we do that? Right, I want to overread. Okay, so let's think about what this setup looks like. And we have to think about not only the order of operations, but where are these pointers in memory? Now, I could draw it out, but it's going to take time, and I think we're cruising okay so far. So what do I need to do to create that setup? I need a valid allocation that is early. Yeah? Because that's the thing that I'm going to overread on. Because I can't use a freed one because it's going to null it out. So I need a valid allocation that's early. So we know this first thing is early. Let's keep this guy around. So I'm not going to free that. What else do I got to do? My goal is to get a next pointer in this index 1 chunk. How do I get a next pointer into index 1? I overwrite.
Write something into 1, but we already freed it.
After I've already freed it, I write something into 1. It's been nulled. So if I, like, for instance, we can do this real quick. P send line, we're saying write into 1. We'll say 64 bytes of size. And then in theory, I'm sending A times 64, right? There, that didn't blow
You
up.
have to read it.
Oh, what do I need to do?
For sending bytes, you need to read it.
For sending bytes. Ah, that does make sense. What am I doing? That is not what I expected to see happen. Free 1, read 1, 64, because that should be reading.
You remove the write.
What did I remove?
Write.
What do you want me to do?
Read. Write, then read.
Write, then read? Okay, you want me to do this? I'm going to write whatever is at that pointer and then read it out.
I'm really confused. What write is?
The literal syscall, read and write.
We are writing, so write will stop, like it will scan it.
Now, read will call read. Write will call write.
So read A64 and then write.
You want read
A64 and then write.
A?
Read 164 and then the next line P send.
Like this?
Right after we send 64 is.
This. Okay, I'm doing something wrong here. Let me think. Free 1, read 164. I'm doing something wrong with my IO. Let's see, does that get there? Okay, that works. That freed. Slot 1 is null. So you're saying I want to just do it from by hand here. I'm going to call read. Into one. Buffering. And then it wants a size, which will give it 64. We're calling read. We give it a bunch of A's. That should frickin' segfault. But it isn't, so we'll just carry on and we'll find out what's wrong. Then you want to, oh, I read into 0. No, I read into slot 1. So then you want to write from right. I'm screwing up. Okay, either, which is funny because like I thought I tested this stuff. Okay, but I got nothing. So I guess that's good. I just don't know where it's reading into because that should segfault because it should be reading into a null pointer. I could GDB it, but that's not the exercise. I don't want to turn this into another stack pivoting extravaganza. So reading and writing here should segfault is what should have happened. There's some bug in my code. All right, so that's why it's not doing it. Because assuming that we are toggling null, then after this free, the pointer that is in slot 1 will be null. So then when we read into slot 1, we'll be reading into a null pointer, and that should segfault. And so that doesn't get me what I want. What I need to get is a next pointer into, well, what? We said that you get a next pointer into something by pushing it onto the T cache when there is something next. When I'm freeing in slot 1 here, is there something next? So what is the next pointer going to be? It's going to be null. So I need to put something onto free something into the T cache so that there is something to be a next pointer. So I actually need to malloc a third chunk. So let's malloc something into slot 2 here. Can I free it right here?
No.
Why?
Because then slot 1 can use it.
Right. If I freed slot 2 right here and then malloced it, I'd be mallocing and freeing it, putting it in the T cache, and then this malloc is just going to pull that same chunk back. So I have to do my mallocs together because I want these to be distinct chunks. What order do I need to free these things? And why?
Free 2 and free 1.
Why? The statement was free 2, then free 1.
Yeah, because free 2 puts the slot 2 in the T cache.
Okay.
And free 1 pushes it forward, and the next of the 1 would become 2.
So the statement was free 2, then free 1. And the reason for that is when we free 2, that puts it at the head of the bin. So then when I free 1, there's something already there. So when we push 1 onto the head of the T cache, the address of allocation 2 will be the next pointer that is written to 1. Okay, so now I can do my overread. What am I overreading from?
0.
Right, the statement was a reading from 0. So I need to p send line. This is actually not read, it's write because reasons. We're going to go with, again, our 100 bytes. And then we have our p interactive, except we already had this. P clean, p leak equals p receive until write. And then we'll import IPython and have the IPython embed. All right, let's see if that behaves as when expected. Okay, a whole lot of warnings, but warnings are just a suggestion. And when we get our leak, what we see here, okay, so I leaked. I didn't do my IO well. Like the IO is good. Like the address is hiding. It's hiding over here somewhere. But it's you can't see that very well, right? So I didn't do my like receive until slot 0 new line. I just did p.clean. So we'll receive until slot 0. And then we'll p receive line. That should eat that garbage. And then we receive until.
That's fine.
What did I miss?
Bracket for slot 0.
That doesn't matter. That all gets eaten right here. Now, typing receive line correctly absolutely matters. Okay. So now I don't have that early noise. And here is my address, my next pointer. If we were to take that, and we could do the math, right, and say, okay, this from that pointer, it should be, what would it be? At 64 bytes plus something. So if we were to take leak, what do I want? 64 onward? Is that right? And then I have to do another 8. See if I can do this math right. That is my previous size, right? That's my Q. This right here should be a heap pointer. If we say pointer equals this thing, is that 8 bytes? Probably not. Okay, let's take pointer, let's adjust it to 8 with null bytes. And then use 64 it, gives me a number, we hex it. Okay, I have this. Now my claim is this is a heap leak. Let's see if I am correct. PS AUX grep a.out. Let's find this process. I actually don't know which one of these it is. That is no bueno. I don't need this thing anymore. Right, this was my toy example. Okay, we see 2039, so we'll sudo gdb a 2039, not gab, gdb, and this was my address. And we see that it is in fact a valid heap pointer. Question?
I didn't understand the last instruction.
You don't understand the last instruction
Code.
in the code.
Is that right here, the right 0, 100? How is that leaking?
Okay, how is write 0, 100 leaking the address was the question. We can get there. I have to scroll up a bit in. Oh, I'm not going to get that. Okay, we can get there. So if I do heap bins, I have 2 free chunks, right? That matches what we did over here. I freed 2 and I have freed 1. So this address right here is going to be 1, and this address right here is the thing that was in slot 2 that we mounted and freed. Yeah? Because remember, we pushed to the head, so the latest thing on the singly linked list is the first thing that was freed. All right. Now, the other thing I can look at is heap bins, or not heap bins, heap chunks. And I'm gonna have to do a little bit of hand waving here. Oh no, I can get us there. So if I do p send read, what do I want? Read into 0. That was my guy that's sticking around. Let's read 8 bytes, and then let's give it 1, 2, 3, 4, 5, 6, 7, 8. Let GDB do its thing. Keep chunks. Do I see my A's in here? Keep chunks all dash. Oh, I do not. That should be P interactive.
There are some A61.
Yeah, there's some A's, but that's not. So, like right here, what do we see? This is an interesting like anecdote. We see my string read 08 A, right? We are not the only ones that use the heap. What program, process, function likely dealt with this data? So probably not the syscall. So when you do a syscall, you'd go into the kernel. The kernel has its own heap that's separate from what we do. We are not going to cover kernel heap in this class. It's super cool and interesting, but no, it's not the kernel, but it's the right idea. This is likely a chunk that was used by scanf. So it was used by libc in userland. When scanf, I said scanf has to like take in this data and parse it and move it around. Scanf doesn't know how many bytes it has to read to get in, right? So it can't be a constant value that's on the stack. This right here is just some chunk that scanf used on the heap in its implementation. It's actually unrelated to us. So I can't, I'm going to have to do to get us answer your question. Nothing else from Twitch that's good. Is I need to print this stuff. And we will decode this as Latin 1. Because I was just swallowing that before, the earlier output of the challenge. Okay. So now, why did that not print? I did, in fact, say print, didn't I? Print P, receive until, oh, that's going to get eaten right there. Decode Latin 1.
The other closing bracket again.
Quicker than me. Okay, hopefully, yes, we get slot 0's address. This is literally what I wanted. I just wanted this so we can confirm that this is this trunk. All right, so then we had leak, and our claim was these magic bytes here. I don't know how many I got. Beautiful. So we can use 64. Adder, and then hex it. Cool. That's my leak. And then if we reattach GDB, PSAUX, grep ADA out, sudo GDB A2478. Okay. So now I have this slot 0 address. We are writing out from this valid allocation, right? So to STD out. And so if I examine, and we'll do like 40 giant hacks, I don't know if this is enough, from here, this is an allocation, this address is the beginning of an allocation that is supposed to be, what was I asking for, 64 bytes in size? So that's going to be 8, it's going to be here. This is the end of the valid allocation that is supposed to be in use by the program on the heap. But I'm going to keep, go ahead.
Yeah, I will try to see if I'm correct, like if I'm correct. So next is the next chunk that we malloc, but we can see 51 and address there because it is in the T cache. If it was not in a T cache, we would not see those 51 and other numbers that I see.
This is the beginning of the allocation that is currently in use
Okay, so that.
So when we are given a pointer by the heap, and this is where watching Jan's video, super important. Having little drawings of like what is going on here, super important. We in userland get the pointer to this spot right here. But I keep saying I allocated 64 bytes. That's what I asked for. But I keep saying the chunk is hex 50, which is 16 bytes bigger. Why? Metadata. So even when I am holding on to and using an allocation, the heap still has to have metadata. And it hides it behind the pointer that it gives us. So when we say malloc 64 bytes, it gives us this pointer. That's what I threw into slot 0. The heaps implementation says, yeah, you asked for 64. You're allowed to write up to 64 bytes. You can put whatever you want right here as long as we say you own it. And the heap says, we're just not going to tell you, but we're going to have a little scratch space behind that pointer that we use, again, for bookkeeping. So what I am doing when I'm writing out 100 plus is I'm starting from this valid allocation address. I actually can't read backwards, right, in this program. I have to read forwards. And so I read, and I read my 64 nulls that basically do nothing. And then I read my hex 51, which is pointed out was that Q. And then I read a whole bunch more null bytes. And then I get this right here.
That is because that is the T cache.
Yes. Did we free this in the wrong order? We did. We suck. That's why my math wasn't working. So this is actually a next pointer. And this right here is, somebody say it?
Yeah, I was looking at the same thing. One piece earlier, but now it makes sense.
Say again?
So I assume like the keys would have to be like behind the address in the first chunk, but now it makes sense to point the keys at that.
Yeah, the statement was the key, right? So we weren't actually leaking the next pointer, we were leaking the key. And the reason that we did that is because we freed things in the wrong order. I thought we walked through it. We still got it wrong, right? This is why it's important to keep track of what order is what being freed, right? What's the order of the allocations was the order that you're freeing them. Because it turns out we freed this one, then we freed this one. So this is the first thing that was freed with the null next pointer. This is the second thing that we freed with a next pointer that points to this guy. And so we ended up getting a next pointer, but it's not where we thought it was. You ought to fix this? I am at time. Or do you understand what we have to do?
Just read more.
I'm sorry?
Just read more.
So I could, the one statement was I could just read more. And I could. The other thing that I could do.
But it's because you malloc 2 before 1.
So I freed them in the right order. I mallocked them in the wrong order. Good catch. Like one of them had to be wrong there. And that's why it's super helpful to script this stuff. So now let's do that same thing real quick here. PSAUX, grep a.out, sudo gdb a2725, and then let's examine, 40 giant hex at, starting at slot 0, the same thing that we were like roughly looking at. Now this looks same, right? We're starting our leak from here. There's my 64, right? 1632, there's my 64. This is the 16 bytes that the heap has hiding behind the second allocation for metadata. That's why we have the hex 51 there. This is our next pointer. The next pointer is located at the address that is mallocked and freed, right? So there's metadata behind the pointer that you get from malloc, and then the next pointer is literally at the allocation address. And then this is the key. In late challenges, this will not be a heap address. The key becomes a random string of bytes that has no meaning. Just FYI. But for early understanding and learning about the heap, it's way easier if we deal with it this way. So this is the next pointer that we want to delete. And this next pointer is to this address. And so I could know, for instance, the address of my current allocation by doing this, overreading, I leak this address, and then I know hex 100 or hex A0 behind this leak should be me. I don't know if I mapped that right, but there is a constant from this leak, which is this allocation, that would get me to there.
And if we free the zeroth allocation again, because we are doing null thing, it will not work. If we
The statement, this will be the last things I am over time. If we freed slot 0, then the pointer that is sitting on the stack, I don't think this has, yeah, it doesn't. I'll compile it with symbols next time. There is an array. Oh, actually, I think it's in the BSS now that I'm thinking about how I wrote this. So I just have this global char star pointer. I don't really care. That's on the BSS. Right? So there's this array in the BSS that is these pointers. And so when I say we null on free, what's happening here in the code is we call free, and then we just literally set that pointer that's in the array to be null. Right? And the statement was, does that mean that this wouldn't work if we nulled it out? And the answer is yes, because when I try and write from that pointer, it's going to write from null, and it should segfault as a null pointer dereference. All right. With that, I'm out of time. We'll try again next week. Remember, I think there's Holiday Friday.
Just next week.
I don't know. It's coming up and it's creeping. It's going to mess us up. So we'll see what we can do. Goodbye. Good luck, everybody. Thank you for tuning in.